Okay, I thank the organizers, even if I'm sure I'm not right here, for the possibility of giving the second talk in this nice SPD program meeting. So, okay, the talk is, I prepared quite a few slides. I hope I can have time to show you more or less everything. So this is something I did with other people. I will cite them in the order. In the last 2 years, at least. And actually, I would have liked to talk about extension, which is what is somehow work in progress now. But I think it takes too long to get just here. So I will try to go as fast as possible for the first part, but wouldn't like to be completely ununderstandable. So I'm not sure I will actually have the possibility to speak about more recent results. So I have already given this talk 2 or 3 times. I mean, quite closely ready talk quite 2 or 3 times. So if anybody has already heard, I'm just sorry for doubling. I'm not sure I will have time to talk about some new stuff. Indeed, I just give a sketch on the slides. Okay. So first, I would like just to talk about motivation. Our mathematical setting will be somehow different from these, but these are the motivation that made me interested in the program. Okay. So if you take just some random walks, continuous time random walks, x1, x2, an infinite sequence. Let's say on Z, you can do the same on a discrete torus or on ZD, okay? And then you may consider the empirical measure associated to this random walk. So what do? You put a mass 1 over n in the place, first you are on Z, okay? So there are this random walk that jump over Z, okay? These maybe then move here, these maybe then move here at exponential times. Well, maybe the guy who is here, maybe he will move here and so on. And just you put a mass 1 over n at the position of the particle xj, and then you sum over j. But in order to have a non-trivial limiting behavior, okay, if we rescale the space with let's say with speed 1 over n, namely this is z, so we put the mass not where the particle is, but at where the particle is divided by n, okay, so we count the particle at the point xj over n. Of course, if the random walk is symmetrical, usually you will deploy in time t. I mean, you will take it, if each step you make, if the spring of the lattice is of length 1n, which is the same as saying that you put the point at you put the particle at xj over n, you will take usually time n squared t to make a displacement order 1. So if each jump you make is 1 over n, you will take, and the random walk is symmetrical, you will take a time n squared t to make a displacement order 1, to move something order 1. So, I mean, this is just a way of writing this, okay? You count where the particle xj is at time n squared t, and you divide it, you scale the position by n, okay? So, classical results state that when Pn, if the particles are, let's say, independent, okay, independent symbol symmetric random walk on Z, when n goes to infinity, suppose that at time 0, the distribution of particle at time 0 converges in a weak sense to a absolutely continuous distribution on R, function on R. Okay, so you have all these little masses, and when n goes to infinity, you just converge to some profile. Okay, then it is well known and not difficult to prove that the empirical measure at time t converges to still to something which is absolutely continuous with respect to Lebesgue, but is a function of time, and indeed the whole path converges, and not just at fixed time, to the solution of the heat equation. Okay, so this is classical. So what happens if they have non-zero mean, these random walks, this particle? Well, usually if you scale the lattice spring by n, you will take just a time mt to make a displacement order 1. So here the right scaling is just looking at the particle as a time mt. And then now you will converge to transport equation, okay? dtu plus v scalar the gradient of u equal to 0. And now, okay, here let's say we are in dimension 1, so the gradient is just the derivative. And the vector v is just the mean displacement of a single random walk. So now what happens when the random walks are interacting each other? For instance, a very basic model is the so-called exclusion process. So you have these m particles on your favorite lattice, and each particle can jump, let's say you can make it symmetrical or asymmetrical, it can jump left or right with a certain probability, but it is restricted. It tries to jump. If there is a particle that is right, then the site is occupied and it doesn't jump. If there is a particle to the left and try to jump to the left, it's the same, it doesn't jump. So here is just, you see, there are, let's say, three particles, the one marked black, and the particle tries to jump to they always jump to the right in this model. And you see that when there is a particle to the right or let's say they jump clockwise, to the right of a given particle, it doesn't jump. So it waits for the other particle to move before it moves. So it's just interacting. It's just some interacting random walks. Well, the interaction is really somehow easy to understand. The only interaction is that jumps on occupied side are forbidden. Okay. So you can also guess what convergence result do you have for the empirical measure associated to such problems. So the empirical measure, we had two cases, the diffusive scale in which the random walk was somehow had the displacement had mean 0, and we needed a diffusive scaling. And in this case, here is a plus missing. Okay, in this case, you will usually converge. It depends on the model, of course, but you will usually converge. The empirical measure will usually converge to the solution of some parabolic equation of this form. For instance, for the simple exclusion model I just mentioned, symmetric, you up to some constants, you have this. Is it clear? I mean, the interaction gives you some nonlinearities. This is the main idea. Well, if the jumps have non-zero means, then you do the hyperbolic scaling as well. And what happens is that you converge to the solution of basically the Burger equation with the suitable flux. Of course, this is not true in general. This is true for quite wide zoo of particle system models. Or it's just a uniformly elliptic matrix. For instance, you may take about the Laplacian. If D is a constant, here you have just the Laplacian. Otherwise, it's, let's say, something uniformly constant. I mean, it depends on F and U. They depend on the model. For instance, for this model I've just described, roughly described, F is just U1 minus U. And this is just the identity, so you get the Laplacian as operator. So if there isn't, I mean, if the random walk is not symmetric, each particle has not a symmetric behavior. Here it's missing a plus, yeah. Sorry. That's why I wrote the equation again. So this equation is not well posed. I'm going to talk a bit later about this. And it should be interpreted in the so-called entropic sense, okay? But still, you have convergence to this kind of equation. Then, once you have convergence, you may ask about large deviation. So I just recall you the definition of large deviations, and instead of the parameter n going to infinity, here I put a parameter epsilon goes to 0, just because it will be more suitable for what I'm going to say later. So if you have a sequence p epsilon of probability measure on some Polish space X, you say that large deviation principle holds if on closed set you have this upper bound, so namely you need the semi-continuous functional I on your space, so I, oh, it's here. I, it's some function from your Polish space X with values to positive real numbers, possibly infinity. You say that large deviation upper bound holds if you have this inequality on each closed set, and the lower bound holds if you have the inverse inequality on open sets, and you say that large deviation principle holds if you have both. Okay, so I've just I've given the same definition last week, but here, okay, what I'm claiming is that large deviation holds if up to small terms in epsilon, this is something like the exponential of minus a epsilon. So a epsilon is something converging to plus infinity, is the speed of the large deviations, times the infimum over the set M of our functional, where M is a subset of X. Of course, this equality should be interpreted in this sense, and this is an inequality on compact sets and the reverse inequality of open sets, and these two inequalities are exactly the same you get for usual convergence of probability measure. Okay, so usually for a convergence, for a probability measure, you say that P epsilon converges to some P, is the probability measure of some set, a regular set, converges to the probability measure, to the probability, P epsilon of a set converges to P of M. Of course, this is not true in general. You have a bound on open set, another bound on closed set, and the large deviation is just the same, and this is somehow a fine way of describing the asymptotic behaviors of large deviations, okay? Of our probability measure P epsilon. So why are interesting here to large deviation for the empirical measure? The reason is that in statistical mechanics models, the large deviation rate functional gives, in some sense, a suitable generalization of concept like entropy in non-equilibrium models. So the statistical mechanics is is understood. Then there are a lot of models with problems, but it's basically the framework is understood at equilibrium for equilibrium system. While out of equilibrium, even the framework, the mathematical framework is not completely clear, but certainly if we make somehow stochastic models, the large deviation rate functional is somehow it somehow provides tools to calculate, for instance, what should be entropy or free energy for our systems. Okay. For instance, at equilibrium. Oh, okay. So we have this empirical measure. We have our model, particle jumping on a lattice. Okay. We have the empirical measure, suitably rescaled, and we want to investigate large deviations. Okay. So for diffusive systems, so namely when the mean displacement is 0 and we do the diffusive scaling, namely we look the position of particles at time n squared t. This depends on model exactly what you get, but for a wide, for many studied models, the large deviation rate functional has this form. So it is just usually this is, in the hydrodynamical limit, you get that the empirical measure is a solution, converges to a solution to this equation. Okay. Now the large deviation tells you, okay, the cost of deviating from this equation is roughly so the probability, let's say, of finding our empirical measure Pn close to some profile V is roughly e to the minus n, and then that function. Okay. So this function is just how much you violate the equation weighted in some less Banach space. Who is F, who is D, and who is the norm in this Banach space is really model depending. Okay, so it's just this is a very general way of writing the stuff. It's not. It's not rigorous. Not a claim for every model. It's just, for instance, let's say the exclusion process, you have this kind of stuff. Okay? So this is true both for independent random walks and interacting or dependent random walks. Okay, just if you have independent random walks, all this stuff is linear in U. That's the only point. Yes.
Result in nonlinear equation, what you consider? In which class a priori you consider solution? What about initial conditions, L1 or L infinity?
Yes, let's say for the exclusion process, which is somehow what we can keep in mind, we have only one particle per site at most. So the solution is a priori bounded.
But
so it's in L infinity, let's say. Huh?
You don't assume L1 property of solution. Are you working with density, integrable solution, or not?
I'm just giving a very informal review of results. So there are results. I mean, there are somehow. Usually, you have. Usually, you deal with integrable densities, and you have somehow. If you work on Z, on R, let's say you have growth conditions at infinity, but somehow you can prove that this growth condition holds in the limit.
Because you mentioned non-equilibrium system, yeah? And depending on class of densities, we will have completely different system. If you have integrable density, it means that your system effectively has average density 0. Or you will have non-zero density. That's another story. When you have really infinite system.
Yes. But let's say that we deal with, for example, exclusion process. So the density is bounded. So, okay, you are just in L infinity, not in L1, but instead of R, you may consider the torus, the discrete torus, you make the limit, and it's just the same. So there you are L infinity and bounded. This is just, hydrodynamics, and usually the issue when you do this kind of results is you prove this equation. I mean, you prove that the solution converges to this equation by compactness, and then you want to prove uniqueness, and you prove uniqueness by proving uniqueness of the solution to the equation. And even the heat equation, I mean, where it's linear and everything, you don't have uniqueness without any bound. You want some bounds and at the infinity and so on and so forth. So, I mean, this is maybe an issue. You're right, but I mean, I'm just giving a review in the most comfortable hypothesis. Okay. So this happened for diffusive system, which is somehow the easiest case because here you have Laplacians and everything. What happens for hyperbolic system is much more complicated. So if you consider the independent case, you may prove that. Remember that in the independent case, Pn converges to the solution to dtu plus constant vector v times the gradient of u equal to 0. Okay. So now there is a result by Kipnis and Leonard 95. Large deviations are given by how much you violate. I mean, the rate functional is given by how much you violate this equation. Okay. In a suitable norm B of u, which is just related to Poisson processes, it's just an x log x Orlitz norm. So this is it's not a difficult result, but it gives you the idea that now the speed is n squared. So for diffusive symmetric systems in which times goes at like n squared t, the macroscopic time is n squared t, the macroscopic time is n squared t, the microscopic time, you have speed, where is it, n, and here you have speed n squared. So the probability, here it is, while in this case you have the probability of Pn being close to v, the v to u, is about e to the minus n squared, this function e of u. Okay? Where now I is this function. So what happens for interacting non-zero mean random walks? So you have these particles. If they do not interact, they are independent. Here is the result, and it's somehow easy. What happens if they are interacting? If they are interacting, it's really complicated, and there are only partial results. mainly studied by Vardan and his PhD students at Courant Institute. So he addressed the problem for totally asymmetric simple exclusion process, namely the process I showed you before, in which you have just particle always jump. I mean, particles cannot jump with a probability to the left and certain probability to the right. Just jump, let's say, to the right with probability 1 at exponential times. Now, if you want to study large deviation from this problem, it's kind of complicated. Why? Because let's say, for instance, start with independent particles. So you have your n particles, and for instance, you may think that you start with particle, 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 and then everything empty on Z. Okay. So here you have n particles, and so you start. I mean, in the limit when n goes to infinity, you start with a density which is not like that, 0. Then here you start with. You arrive with 1, and then you are 0 again, okay? So what the probability that, for instance, this shape just stays the same? You have n particles, and they are independent, let's say. So you don't want them to jump. You have n particles, and they are not going to jump up to the time nt. Okay, so they will keep the same, and you will have this profile for order 1 time. So the probability of this to happen, and independent particles not to jump for time nt, this is something over there, e to the minus n squared. You have to keep n plus some processes not to jump for time nt. On the other hand, if they are dependent, for instance, you look at exclusion process, okay, so jumps to the right are allowed only if the site to the right is empty. Okay, for this profile to stay the same up to time t, you just say, okay, this particle does not jump for time nt, and this happens with probability e to the minus n. Okay, also depends on t, but let's care just about n. And then all the other particles, they just will not jump. So this will happen with probability 1 if this is blocked. So here, in the independent case, the large deviation just happen on different speeds. So the situation is quite unclear. Vardan and Jensen have done quite a nice work, but it's basically partial and basically unpublished. Because all of these guys left mathematics after their PhD. Yeah, what happened is that I think Jensen, he made a nice thesis, and then the other tried to somehow finish the results, and by the end, all the three of them finished with no publications. And in the States, if you finish PhD without publications, it's very hard to find a job. So here, these were just motivations. I took a while to talk about this, but I think this was somehow important. It was somehow important to me to motivate. I hope you understand more or less what the questions are. If you didn't, it's not important, because the mathematical setting here will be completely different and will be just a stochastic partial differential equation. So
in the top equation, what was V?
Sorry?
What is V?
Oh, V was a constant vector, which was just the mean displacement of each random walk. So for instance, if you move always to the right, here V is just 1, or minus 1 maybe. So I will focus, I would say, okay, we have this Pn, jumps, and whatever. I just want to get rid of all technical details and try to understand what happens. Okay, so this is, I mean, a result concerning this stochastic PDE has nothing to do, mathematically speaking, with jumps, Markov processes, and so on and so forth. But I just wondering, okay, maybe that large deviation for a stochastic PDE may, in some sense, recover at least the heuristic idea of what may happen on particle systems. Okay? So here, let's say, to say simple, let's just consider a one-dimensional space situation, and I'll consider time in a compact, with finite horizon time problem, and x, let's say, on the torus. This holds straightforward if you want to go on R instead of the torus, and the d-dimensional case is not so straightforward, but one can deal with it as well. So what's the equation is dtu plus the divergence of f of u, but in dimension 1 is just f of u x. So this just means, if u is smooth, this just means f of u x, in this notation of the divergence of f of u, is just f prime of u ux. So this is equal to what? This is equal to a small diffusion. You can think d is just the identity, and this is the Laplacian, okay? So it's epsilon the Laplacian, plus epsilon to the gamma, so epsilon to the gamma, where gamma is some real parameter, sigma of u, another function of u, times a noise, and the noise is white in time, and there's a correlation in space. Okay, so this is just, this somehow this comes from the model. You see, ut, you may think of it as ut plus the divergence of some current j equal to 0, where the current is just f of u, which is a flux, plus minus a diffusion, and plus or minus some noise. Okay. Now the the deterministic diffusion and the noise, they are small. This is what happens for particle systems. I mean, fluctuation, they vanish in the limit. In fact, we saw that the empirical measure converge to some deterministic profile, the solution of some PDE. And for asymmetric system, the one that have non-mean zero, the viscosity, the diffusion, the deterministic diffusion is vanishing as well. So the noise and the viscosity, they vanish in general on different scales. Okay. So for instance, as I said, sigma may have a compact support. This is, okay, let's skip this kind of details. So, on the general hypothesis, there exists a unique smooth solution u epsilon to this equation. This is a first result, if you want. This existence is not really straightforward, because you see there is a derivative in space on the noise term. So the quadratic variation of this noise actually has some derivative of u in the quadratic variation of the noise here. If you derive roughly, this gives you the sigma prime of u ux plus the derivative times the noise plus sigma of u, the derivative of the noise. And the term in which there is a derivative on u is somehow, the quadratic variation of this one is comparable with the quadratic variation of this, with this term. So the good diffusion fights with the noise in the existence. And indeed, actually, you have existence for epsilon small enough, where since this gamma is larger than 1, this noise will be small with respect to the diffusion. Actually, you can prove, even in the linear case, but where sigma is non-constant, if sigma is non-constant, you can prove that if you take epsilon order 1, in general, you have no existence. So there are results of non-existence for this kind of equation. Okay? So, and as I said, this is a stochastic conservation law in the sense that it's a continuity equation for you where the current is random. Okay? So the idea, to connect with the motivation before, is that the empirical measure associated to some interacting random walks, for a reasonable model, let's say the exclusion, it's close to the solution of the stochastic PDE when epsilon is small with n. So epsilon is n to the minus alpha, where alpha depends mainly on dimension and other feature of the model. So the idea is, okay, in the limit, when epsilon goes to 0, in fact, the empirical measure converges to the solution to this equation where you put epsilon to 0 here and here. And this approximation is somehow a mesoscopic approximation of the problem. Instead of having and particles which jump randomly and that in the limit converge to something deterministic, you say, okay, I just say at fixed n, at fixed epsilon, they are not really particles, they are already some density, okay, this is a mesoscopic approximation, but this density has a small diffusion, a small noise, is still stochastic, okay? So in order to deal with the large deviation for this kind of problem, I just would like first to introduce some preliminaries, okay, on what's the meaning of solution to these equations and so on. So is it clear? Yes?
The solution considers sign, so you can consider it as a density, or
Sorry, the solution is?
does not conserve the sign. I mean, if you choose, if you say you choose sigma in a good way,
So
so you can say that U is really a density.
U is actually a density. I mean, it has the solution to this equation is a function, it's not a measure. If the point is, if sigma has compact support, maybe it's what you are. If sigma has compact support, something like this, you can prove that if this, so let's say that sigma is supported on some interval, let's say 0, 1. This is the case if you want to model the exclusion process. So sigma of u is something like, or sigma square of u, let's say, is something like that. Okay. And if the initial condition is something between 0 and 1 as well, okay, then you can prove that for a positive time with probability 1, the solution is between 0 and 1. Because you see, if when u is out of sigma, when u is out of the support of sigma, you just have there is no noise, so you just have a parabolic equation, a fixed epsilon, and it satisfies maximum principle. So let's say as soon as you get out of the support of sigma, you have maximum principle. And this, okay, inside the support of sigma, you have not, so it's not true that you have somehow attractiveness. But as soon as you get out, this is the case. So if you start with u between 0 and 1, you stay in 0, 1. For instance, for the exclusion, it works. Okay?
So even inside the support of sigma.
If times 0 you are inside the support, let's say the sigma is not like this between 0 and 1. Okay. At time 0, u0 only takes values in 0, 1 for each x. For instance, you start with the constant 1/2. Then the solution to this stochastic differential equation is always takes values, probability 1 takes value in 0, 1. Because the noise, basically, when you exit from the interval, there is no noise. Okay? So, I mean, this is a bit delicate because also for random, for okay, also in dimension 1, it's a bit delicate. I mean, you need some smoothness of sigma to really have this result, but this is the case. Okay, so it's okay. This is the equation. It's dtu plus the divergence of the flux equal to a small diffusion plus a small noise, and the noise is also a total derivative in x of something. Okay. Okay. Oh, this is the last assumption is that so who is W epsilon? W epsilon is just what in time W dot. And in space, there is a correlation, which I think is obtained as a convolution of some smooth kernel with a cylindrical Brownian motion. And as epsilon goes to 0, J epsilon converges to a delta. And actually, it has to converge fast enough. So in order to investigate what happens when epsilon goes to 0, I just recall some results for the equation which you formally put epsilon to 0. So if f is linear, it's just a transport equation, and if, for instance, the vector field is constant, so there are no problems of existence or uniqueness. If you start with some profile, in the independent case, so in the case f equal to some constant times u, you start with some profile, and at time t, you just will be shift of this constant c in time. Okay, but if f is nonlinear, what happens is that now f of ux is f prime of ux. So each point of the profile will move with speed f prime of u. So different points here will move with different characteristic speed. So you start with this profile, and this point will travel with speed f prime of u, where u is here, and this point will travel with speed f prime of u, which is, let's say, much faster. So after a finite time, you will drop on something which is not like this. I mean, this flux, dtu plus f of ux, develops singularities. This is well-known behavior of, let's say, Burger equation. Okay? So what happens is that usually you have to interpret this equation in a weak sense. I mean, you just integrate the derivative in time and in space against x function. You say that a solution is a solution if the integrated form is 0. Okay? But in this sense, there are infinitely many weak solutions. So there is a classical result by mainly Khrushchev and Tartar, I mean, the uniques and existence, respectively, that tells you the following thing. Okay, you just take a convex function eta of u, and let's define q of u like q prime equal, by the relation q prime equal to eta prime f prime, where f was the flux, okay, f. Then there exists a unique solution, u bar, which has this property. The derivative in time of eta of u bar plus the derivative in space of q of u bar is negative. Just a remark is that if u is smooth, dt eta of u plus q of u, q eta of u derived with respect to x is equal to eta prime of u times dtu plus f prime of u plus f of u x. So if you can apply chain rule here, you just get this by the definition of q. And so this is, if u is a solution, smooth, this is 0. However, since there are not in general smooth solutions, what you can see is that in general this is not 0. If your solution has a jump, this quantity is not 0 at the jump, because this chain rule doesn't hold in general. So the point is, what's the entropic solution? What's somehow the relevant solution to this equation? Is a solution such that this distribution, dt eta of u plus q of ux, is negative in sign. So when you integrate these against positive tensor function, you get something negative, okay? So the point is here, this equation, here, it has space-time symmetry, okay? Eta is if you change t minus t and x in minus x, the equation stays the same. So the entropic condition for, oh, maybe I didn't mention this properly, eta should be convex here. Of course, if you change eta and minus eta, this distribution changes sign, so you ask this for convex function eta. So this condition somehow breaks this space-time symmetry and tells you in which sense time is flowing, in which sense you should continue this equation when you have some discontinuity. So the classical result is, okay, there exists a unique solution entropic, namely with this condition. Okay, entropy is dissipated. This distribution is negative. And why it is somehow the physical solution? Because if you have a real fluid dynamic equation in which you have some diffusion, some Laplacian, when epsilon goes to 0, the solution to this equation converges to the solution to this equation, the viscous conservation law. Okay. So it's so-called also admissibility formula. When you have shocks, it tells you how to continue. So a first result for the stochastic PDE is a law of large numbers. Namely, when epsilon goes to 0, the solution to the stochastic PDE converges strongly in LP, but also in weak continuous in time topology, to the entropy solution of the viscous equation. So basically, in this equation, it tells you can put in the limit you can put formally epsilon to 0, provided you interpret the limiting solution in the right sense, the entropic one. Okay. And this is heuristically, this result is equivalent to the hydrodynamical limit for Pn. for the empirical measure, I said, okay, when n goes to infinity, you have an hydrodynamical equation. The empirical measure converges to a solution of a PDE. And this is the same for U epsilon. So this is somehow equivalent in this heuristic equivalence between stochastic PDE and particle system to the hydrodynamical limit for PM, to the low order numbers for the empirical measure of random walks. So now I want to look at large deviations. The setting for large deviation is a bit complicated. So in order to study large deviation, what happens here is that large deviations are somehow, you investigate the probability of sets with small probability. So if you look at a set with small probability, I will investigate the word small in different sense. So in the first sense, this noise, which is small with high probability, can be order 1 with small probability. So in the limit when epsilon goes to 0, this noise will stay order 1, while the smooth viscosity will drop to 0. So what happens is that the noise with the probability small but order 1 on the large deviation scale can somehow make oscillate the solution U epsilon fast. You have no smoothness at all. So the large deviation principle should be investigated on a space of Young measures. Okay? So what happens, you just lift this equation to the Young measures, namely for each epsilon, you consider the Young measure nu epsilon Tx, which is just at each point Tx. You consider at each point Tx, you put a measure, which is just the Dirac delta at the point U epsilon of Tx. Okay? This is the usual setting for Young measure. Now, on the set where nu epsilon lives, which is just the set of maps from 0t times the torus with values in the probabilities on 0, let's say on R, on the here the 0, 1 is not correct. So it's the set of maps from Tx to the space of probability measure on the set where U takes values. Okay, so for each epsilon, this nu epsilon is actually a delta on U epsilon, but in the limit, you may converge to whatever Young measure. Okay, so plus some continuity assumption just to fix the need. I mean, the space also has some weak continuity in time. I'm not going to specify what's that. So, are you familiar with this Young measure setting? No. So it's just for each U, for each epsilon. This is not a stochastic issue. For each epsilon, you just consider U epsilon is a function. U epsilon is a function. So you consider a measure which so you have your space. Let's say you have time and you have your torus space. So at each point Tx of the space, you put a measure, which is just at fixed epsilon, it's just a delta on U epsilon of Tx. When epsilon goes to 0, U epsilon typically will converge to U bar, but with small probability, it can oscillate. So in the limit, this nu epsilon, if U epsilon oscillates, it may converge to some measure, to some Young measure, so namely to some object that on each point of the space T and X is not necessarily a delta on some values U, but it's just for each T and X, just a probability measure on, let's say, R, if U takes values on R. It's just, for instance, if you consider a function f of U epsilon, if epsilon converges strongly in LP to some U, then this will converge to f of U. But if U epsilon doesn't converge strongly to some U, this will not converge to f of U. This will converge to nu of f. So the main point, the main point here is, if epsilon goes to 0, you just forget of the viscous term of the deterministic diffusion, and you write dtu plus f of u with a notation of Young measures, you take the limit where epsilon goes to 0, and you obtain how much the equation is violated. So how much? So I mean, if nu now is really the delta on some u, which is not necessarily the case, nu of I is just u, and nu of f is just f of u. But in general, for a generic Young measure, this is not the case. I mean, this is how you would write the equation in a space of Young measure. So the statement is p epsilon satisfies the Large deviation principle with speed epsilon to the minus 2 gamma and rate functional, which is how much you violate the conservation law in this Young measure setting. Okay. For instance, if f is linear, this is equivalent to, I mean, the heuristic equivalence between u epsilon and Pn, the empirical measure. This is equivalent to the large deviation results of Kipnis and Leonard. And how much you violate in a suitable Hilbert space, which depends on nu of sigma square. This is somehow if you are a bit familiar with large deviations and with the Friday-Wenzel result, this is just a restatement of Friday-Wenzel for Young measures. So the speed is just the square of the coefficient of the noise. This doesn't matter in the limit, epsilon the viscosity. And so you take the cost, I mean, the cost function in the limit is just how much you violate the deterministic drift, measured with the normal, which is dual to the quadratic variation of the noise. And in the limit, this J epsilon, which is mainly used for existence, doesn't matter, the convolution. Okay. So this is just a way. But what's the point? As I said before, this equation doesn't have a unique weak solution. So it absolutely does not have unique measure valid solutions. Namely, as long as you interpret this equation weakly, you already don't have uniqueness. Now we have to interpret this, in order to establish the large deviation principle, we have to interpret somehow the equation even on a Young measure setting, which is a much bigger space. So in this setting, you don't have uniqueness of the equation, of this equal to 0, and so this functional I of nu, the rate functional for the large deviation, it has a lot of 0. All the measure valid solution to the conservation law are zeros of this functional. So what happens is that you want to investigate a second order large deviations principle. So somehow what happened is that, okay, on this scale, epsilon to the minus, we looked at probability of the solution u epsilon to be close to some measure, to some Young measure. And namely what happened, we established a result in this sense. The probability p epsilon that the delta over u epsilon is close to some given Young measure, this is about the exponential of minus epsilon to the minus 2 gamma. Epsilon to the gamma was the coefficient in front of the noise. This rate functional calculated at the Young measure nu. Okay, this was roughly speaking, in the sense of large deviation, this is the bound. But now we know that this is true, but we know that for a lot we know that u epsilon converges to the entropic measure, while this stuff, it has a lot of zeros. So what tells this equation is that this equation tells us that if E of nu equal to 0, the probability that the delta of u epsilon is close to nu is roughly 1. Well, this is not really the case. It tells you that the decay is not exponential with this rate, if the probability of being close to a 0 of the functional. So this statement is true, but still it's not very detailed. Okay? We would like to write something like this with a functional which has only 1 0, the entropic solution to the equation. So this doesn't happen with this speed, epsilon to the minus 2 gamma, the Freyde-Vincenz speed. We have to investigate slower speed. So we have to look at sets which have a small probability, but not small exponential to the minus epsilon to the minus 2 gamma, but with some slower probability, with some slower rate. Okay, so that's what I said exactly. So in order to do this, I have only 10 minutes left. We need to do some other preliminaries on the. I mean, we have to introduce a suitable class of solutions to the inviscous conservation law, the one with epsilon to 0. Okay. So remember that an entropic solution was a solution such that this distribution was negative. Okay. Now we concentrate on a different kind of solutions. The solution for which this is not necessarily negative, but in general is a random measure. Okay? So if this is a random measure for each eta convex, you can prove that there exists a measure Pu, which depends only on u, which depends on P, and u is a weak. If u is a weak solution, and this such that this distribution is a random measure for each eta convex, there exists a measure which is a measure on time, space, and the level sets of u, such that this distribution calculated on a test function phi is just the integral with respect to this measure on the three variable of the second derivatives of eta calculated at v times the test function. It's clear that this should depend, I mean, that this distribution is linear in eta, and actually if you change eta by enough in parts, this distribution will not change at all, because, you know, if I have dt eta of u plus q of u x, and u is a solution, if I change eta to eta plus alpha u, the distribution will change to dt eta u plus q of ux plus alpha dt u plus f of ux. So if u is a solution, this is 0, and the distribution is the same. So it's clear that this distribution depends somehow on the second derivative of eta, and you can prove that it's indeed somehow a measure with respect to the second derivative of eta. It's somehow just a Banach-Steinhaus theorem. It's not very deep. So, okay, so the statement is the following. Consider this function. So remember these, the stochastic PDEs, okay? There was a flux F, a diffusion coefficient D, and the fluctuation coefficient sigma. Consider this rate functional, h of u, which is plus infinity if u is not an entropy measure solution, namely if these distributions are not a measure. These are distributions in general are order 1 distribution, but consider the class of entropy measure solution, namely the class for which this stuff, this distribution is a measure, is a random measure for each eta convex. Okay? So how much entropy you create is a measure. Then consider the rate function h of u, which is plus infinity if u is not an entropy measure solution to the equation, and is the integral with respect to the positive part of this measure of d of v of a sigma v squared. So for instance, if u is an entropic solution, this means that this distribution is negative. This means that this measure for each eta convex, so here there is something positive somehow, and this, so being entropic means Pu, this measure on time, space, and level set of u, is negative. So the positive part is 0. So h of u for entropic measure, for entropic solutions to the limiting equation is 0, while it is, and since there is only one solution which is entropic, this h of u is strictly positive as soon as u is not the entropic solution to the equation. Okay? So this is, somehow, the idea is that you have shocks. The entropic solution, in the entropic solution, the shock, for instance, if the flux is convex, they are always increasing or decreasing. This tells you, okay, you may consider also solutions for which these shocks are, let's say, increasing if the entropic one is decreasing, but this will pay a price. This happens with a small probability. So the large deviation is, consider large deviation with speed epsilon to the 2 gamma minus 1. So first we consider events with a decay epsilon to the minus 2 gamma. Now we consider events with speed epsilon to the 2 gamma minus 1. First issue is, okay, with this speed, you don't need to consider Young measure. Namely, you can consider large deviation on the space on Young measure, but the rate functional will be always plus infinity on Young measure, which are not delta on some functions. What happens is we have an upper bound with speed epsilon to the 2 gamma minus 1 and rate functional h of u. The lower bound, so you remember for large deviation you need to bound, this is established with the functional h hat of u, and unfortunately one cannot prove that h hat of u is equal to h of u. I mean, they are equal if u is in BV, and one can conjecture that they are equal in general, but since there is not, I mean, one has this representation of chain rule only for BV function, so there is an open issue in geometric measure theory, is to establish a divergence measure, a chain rule for divergence measure fields on. And this is, I mean, if this result is proven, we basically have large deviations, and there are a few people who work recently and even not recently on this stuff, but I don't know if you know fine properties of BV function. There is all these issues with approximate continuity, H1 rectifiability, and so on and so forth. You can do the same for divergent measure fields, but in a weaker sense, only in VMO, and this is not enough to prove this equality. So I strongly believe that the two are the same, but you can prove it only on a very large set, all BV solutions, but unfortunately, I have example of solution, entropy measure solution to the conservation law, which are not BV. Still, on that solution, I can prove the equality, but I cannot prove for all. So it's just 4 minutes. And okay, this is on PTRF, and other people we investigated the closed relative variational problem, which is somehow a variational counterpart of these large deviation results. So the proof is skipped, is basically based on some variational arguments, in fact. And the idea is a generalization of this result in which you look, I mean, you want to make a similarity between empirical measure and solution to stochastic PDEs in the case of long-range interactions. So for instance, instead of a Laplacian of u epsilon, you put just a fractional power of the Laplacian. And the noise, it has a quadratic variation, which is somehow in the same space h alpha, where the Laplacian power alpha holds. And so the main idea is that in this case, you obtain still one bound, not the two, I mean, still with different upper and lower bound, or a priori different upper and lower bounds. You obtain a large deviation rate functional with the same rate, so that it's a sort of universality of this rate function. I mean, the entropy, this rate functional, if you have a closer look, is just how much entropy this solution produces. An entropic solution just dissipates entropy, but what you pay on the large deviation scale is how much entropy the solution produces, speaking in physical terms. So but the idea is that everything holds for no local interaction, and indeed even for very general Fourier nonlinear operators, this functional is somehow really stable. And this also suggests what large deviation should be in what an Einstein relation should be in this long-range setting. But this is, I mean, if somebody is interested, I'm happy to talk about this. I would be glad. The only remark I want to do in the remaining 1.5 minutes is that what basically this result proves is that the probability that u epsilon is close to some trajectory, okay, this tells, okay, this is roughly speaking the exponential of minus epsilon to the minus 2 gamma. First, the first rate functional on, okay, delta over this trajectory. This is a bit not really true, but I mean this should be interpreted in a Young measure space, plus this h of v, plus epsilon h of v, because the second large deviation functional was proved with speed epsilon to minus gamma plus 1. So the point is, this is 0 very often on measure value solutions. So this has a lot of 0. On all these zeros, you have to have a look at the next order. So on this next order, h of v has only one 0, the entropic solution, so other rescalings are somehow trivial. This is the next order one has to look at. And this gives you somehow the cost of solution which paid 0 on this order. And if you look, the equivalent for instance, this explains somehow what the phenomenon that I described before, in which for non-interacting you had a speed of large deviation for independent random walk and another speed of large deviation for interacting random walks. Because what happens is that f is linear, also this functional on Young measure, it has only one 0, the transport equation. You have the transport equation is well posed. You don't need the entropy formulation with solution. There is only one solution if f is linear. However, as soon as f is nonlinear, the nonlinearity of f is actually an hypothesis. I mean, to prove this, it was written somewhere. You need that f is genuinely nonlinear. I mean, you cannot have these. You only can have this. And so in some sense, if f is nonlinear, you still have large deviation with speed n square in the interacting case. But it has a lot of zero on this scale, a lot of paths, a lot of solutions pay 0, and so you also have non-trivial large deviation on a finer scale. In the interacting case. For the non-interacting case, on this scale you will always space plus infinity because there is only one solution. There are no entropy measure solutions which are not entropic in some sense. But in the nonlinear case, you have both the scales. So this is the scaling which Vardan has studied deeply, and okay, I think this is really the case also for Markov processes. You should really have two scales, one on speed e to the minus n square with the degenerate rate functional, and a most interesting one, I guess, on this entropic scale. So, that's it.
Any questions? Okay, thanks, Jan.
There is a question.
Sorry. I just read what you have written on the last page.
Yes.
So does it imply that in the case of Burger's equation, your noise is not white, space-time white noise, even in one dimension?
No, it's not space-time noise. But this is somehow the case for this model. They have a real and spatial correlation.
And in this work in progress, do you have any? Can you say anything about alpha? Do you have any condition on alpha?
Let's say that if alpha is strictly larger than 1/2, I mean, indeed, we do this on some wire space. So if this wire space embeds in HS with f larger than 1/2, we can do it. And if S is smaller than 1/2, I think we can do it. But it's there are continuities in time issues, and of course the two cases are known to be different and should be treated. I mean, the case alpha is smaller than 1/2, it's much more delicate, and I'm not sure one can really deal with the case.
With f of u square.
With whatever, indeed, you don't even need this f of u form here. You can with whatever f of u. With okay, reasonable conditions at infinity, which you square it's fine. I think if you grow faster, it's not fine. No, but I mean.
Yeah. Okay.
Okay, then, thanks again.